In this lesson, we'll continue with understanding how process management works, and we're going to delve a bit more deeper into how different scheduling algorithms in particular work and how they allow processes to be managed efficiently. In particular, we're going to be looking at 4 common algorithms, and they are first come, first serve, the shortest job first, the shortest remaining time first, and round robin algorithms. You're also going to develop an understanding of how the kernel of the operating system acts as an interrupt handler and how interrupt handling is used to manage low-level scheduling, especially in these algorithms. Now, in the previous lesson, we looked at 3 possible states: the ready state, the running state, and the block state. Now, the running state is when the processor is actually executing the instructions. So we need to build 2 queues to support it, and they are the ready queue and a blocked queue. Now, to look into this particular concept a bit more in depth, consider what happens during a round robin process in which each of the processes end up having the same priority. So let's just suppose that we've got processes P1 to P6, not necessarily in the same order in the ready queue. And P1 and P2 have been completed. P3 is being running on the CPU, and certainly it needs to wait for an input. So P3 gets moved to the block queue. Then the next in line, P5, gets his chance of running on the CPU, and that gets executed, and there is no other part for P5. It's executed in the time slice, then that's finished. Then the next one comes in, which is P6, and then the next one comes in, P4, and P3 finally gets the input that it needs, and then that's moved to the ready queue, and then that's moved to the CPU in due course, and once it's completed, the process is finished. So the process state changes need to be managed, but how do we ensure that these processes are efficiently managed? That's the role of the scheduling algorithm. So let's first of all start with the round robin one, since we mentioned it already. What's the process description for round robin? How do you explain it? Well, each process has an equal time slice, which is known as the time quantum. When a time slice ends, the low-level scheduler puts the process back into the ready queue, allowing another process to use the CPU. And you'll probably find that sometimes you have very large processes which don't really fit in the time slice that you've allocated it. So for example, if P1 is a massive program, you might just give it a short time slice, and once it finishes its time slice on the CPU, you then send P1 back to the end of the queue, the end of the ready queue, and that allows it to then have another go at it. In the meantime, its states have to be saved in the process control block, so you can reload it when its turn comes up next. Now, typical time slices are about 10 to 100 milliseconds long, and that might seem a bit low for us, but when you consider a 2.7 gigahertz clock speed, that means that about 100 milliseconds of CPU time is equivalent to 27 million clock cycles, and that's a phenomenal amount of processing time. Now, we already talked about that when a time slice ends, that the status of each process must be saved so it can continue from where it's left off when it gets the next time slice. And these are the contents of the CPU registers, for example, the PC, the MAR, the MDR, the accumulator, and all of these are saved to the process control block. And each process gets its own control block, so you don't end up confusing different values in the registers. When the next process takes control of the CPU, its previous state is then reinstated and restored, and this process is called context switching because you're switching the context from one process to another. So P1 is running on the CPU. When its time finishes, all the states are saved into the PCB, and then the P2 runs on the CPU and it loads its states from the PCB, and those are processed, and then those are then saved back again to the PCB, and then P3 comes in, and so on. Now we will consider 4 examples of scheduling routines, and they are first come, first serve, shortest job first scheduling, shortest remaining time first scheduling, and round robin. And these are some of the most common strategies used by schedulers to ensure that the whole system is running efficiently and is in a stable condition at all times. It is important to consider how we manage the ready queue to minimize the waiting time for a process to be processed by the CPU. You don't want processes to be waiting around forever, so these algorithms support that. However, some algorithms work more efficiently than others, and you will need to work out the waiting time for these algorithms. And we're going to be looking at that next. So let's start with the first come, first served scheduling algorithm. Now this is similar to the concept of a queue structure, which uses the first in, first out principle. Data is added to a queue first, is the data that leaves the queue first. So we've got 4 processes here, P1, P2, P3, and P4. We're going to be using these in the remaining algorithms as well. And they have a burst time of 23 milliseconds, 4 milliseconds, 9 milliseconds, and 3 milliseconds respectively. What that means is that this is the amount of time they need on the CPU. So the ready queue in first come, first served scheduling will be that P1 arrives first, so it takes the full 23 milliseconds. Then the next one arrives P2 with 4 milliseconds, then the next one P3 with 9 milliseconds, and the next one P4 with 3 milliseconds. So the total time in this case is 39 seconds, which is what will be required for all 4 processes to be completed on the CPU. But the average waiting time for a process can be calculated by looking at the start time of each one. So P1 begins at 0 seconds, P2 begins at 23 seconds, P3 at 27, and P4 at 36. So you add all of that up and then divide by 4, which gives you 21.5 milliseconds as the average wait time, which is a long wait time. And wait time basically identifies how long processes need to wait before they can get on the CPU. There is something else called a turnaround time, which looks at the completion part. And if you were going to work that out, you look at the finishing times rather than the start time. Now the next 2 algorithms, shortest job first scheduling and shortest remaining time first scheduling, are the best approaches to minimize the process waiting times. SJF is a non-preemptive one and SRTF is a preemptive one. So what does all of that mean? Well, the burst time of a process should be known in advance. So you should know that P1 will take about 5 seconds to execute on the processor, P2 will take 3 seconds to execute on the processor, and so on. That might not be possible in all cases, but for the majority that would be true. So the SJF frankly doesn't care about the different processes, it just is interested in their burst times. So as processes arrive, it just orders them according to their burst time, with the smallest at the front and the largest at the back. And based on that, it creates a schedule. So if you consider the same 4 processes and the burst times as the previous example, P1 to P4 with P1 having the largest burst time, the schedule is now quite different. P4 will go first, then P2, then P3, and then P1. So now you can see that the start times for each algorithm are slightly different. You do exactly the same as previously, add all the start times, divide by 4, and you end up with a wait time of 6.5 milliseconds, which is a lot more quicker than FCFS. Now the shortest remaining time first scheduling algorithm, on the other hand, uses a different way of calculating the order. The processes are placed in the ready queue as they arrive, but when a process with a shorter burst time arrives, the existing process is removed or preempted from execution. The shortest process is then executed first. So if you consider the same 4 processes, and we're going to add a bit more information here, which includes their arrival times. For example, P1, P2, P3, P4 don't arrive at the same time, but they arrive a millisecond after each other. You can see how the context will change. So P1 arrives, it's got a burst time of 23, it's the only one in the list, so we're going to start with P1 first. And then a millisecond later, P2 arrives. Now P2 is the shortest on the list, so we pause P1, save all the states, all the registers, all the information in the PCB for P1, and P2 gets its time with the CPU. Now a millisecond later, P3 arrives, but P2 still has the shortest burst time because it's got 4, P3 has got 9, so we continue with P2. And a millisecond later, P4 arrives. Now P4 has a smaller starting burst time than P2, so the algorithm alters the schedule and P4 goes first. Now SRTF doesn't take into account the fact that P2 already has got 2 cycles completed, so technically it's the shortest one. It just relies on the starting burst time to keep things simple. However, there are other algorithms out there that modify SRTF to take into account that particular change in context. So our schedule now looks like P1 followed by P2, then P4, then back to P2, which becomes the shortest at that point in time, then P3, and then finally back to P1. So the average waiting time for a particular process is a lot more shorter compared to the previous two algorithms. So how do we calculate this average waiting time for SRTF, which seems a bit more complicated than the previous ones? The simplest way to calculate this is to create a table. And if you look at the table that's been created on screen for you, this will make more sense. So the processes P1 to P4 are listed along with their arrival times, along with their burst times. Once we have this information, we can now calculate the turnaround time, which is simply the completion time minus the arrival time. So for P1, it's basically 39 minus 0, which gives you 39. For P2, it's 8 minus 1, which gives you 7, and so on. And finally, once you work out the turnaround time, the waiting time simply is the turnaround time minus the burst time. So for P1, it's 39 minus a burst time of 23, which gives you 16. For P2, it's the turnaround time, which is 7 minus 4, which gives you 3, and so on. And once you've got all 4 waiting times, you can just simply add them up and divide that by 4, which will give you 6.25. That's the simplest way to work out waiting time using SRTF scheduling algorithm. The final algorithm we're going to look at is the round robin. You're already familiar with this one from earlier. A fixed time slice is given to each process, which is known as the quantum. Once a process is executed during its time slice, it's removed and placed back in the ready queue at the end. Then another process from the ready queue is executed using its own time slice. Context switching is used to save the state of preempted processes. The ready queue is worked out by giving each process its time slice in the correct order. So if a process completes before its time slice, then the next process is brought forward from the ready queue. So you don't necessarily need to use the allocated time slice. You can finish it earlier. So let's fix the time slice at 5 milliseconds. Same processes, same burst times. So the schedule looks like this. P1 arrives first. We use the first time slice for P1, then P2, then P3, then P4. Now you'll probably see that P2 finishes within the time slice a bit more earlier. It doesn't require the entire 5 milliseconds because it's only worth 4 milliseconds. So we bring P3 forward. So instead of starting at 10, it starts at 9. And then it goes to 14. P4's got a very small burst time, so it doesn't require the entire 5 milliseconds, and it finishes in 3 milliseconds. Then P1 kicks in, and then P3 kicks in because it's got some time remaining, and then the remaining ones are P1. Now once we get the schedule planned, we can work out the wait time pretty easily. P1, the wait time is the finish time minus the burst time. So 39 minus 23 gives you 16 milliseconds. For P2, that's the same. P2 finishes at 9 minus 4 for its burst time gives you 5 milliseconds. P3, the end time, it finishes at 26 milliseconds. Subtracting the original burst time of 9 gives you 17 milliseconds. And for P4, it's 17 minus 3, which gives you 14 milliseconds. Once you add all of these up, divide by 4, gives you 13 milliseconds. Now, if you're looking at all 4 algorithms together, you can see that SRTF gives you the most efficient management of processes. 6.25 milliseconds is the average wait time. That means the process gets CPU time the quickest using that. Now, why do we need all these different types of algorithms? Because there are different contexts in the real world. Sometimes you have different types of processes which need to access a FCFS type scheduling algorithm, so you could address tasks first in order of arrival. You want to complete a task first before you address the next task, because perhaps the next task depends on the previous task. So those kind of situations, FCFS, even though it's not the most efficient, might be suitable. Now you probably have noticed that certain scheduling algorithms require different processes to be loaded multiple times. So P1 might go to the back of the ready queue, and then it's loaded up again on the CPU. So the various different registers need to be saved in its PCB. And for that to happen, the CPU will use interrupt signals. And interrupt handling is an important part of the OS kernel to ensure that the queues operate smoothly. So the CPU checks for interrupt signals. The system will enter the kernel mode if any of the following occur. You get a device interrupt. For example, a printer is out of paper, a device is not present, and so on. An exception occurs which could include faults like division by zero, codes which are not recognized, stack faults, and so forth, and software interrupts or traps. For example, a process requesting a resource such as a USB disk which you've unplugged. Whatever type of interrupt that is received, the kernel will have to consult the interrupt dispatch table, which links a device description with the appropriate interrupt routine. So it is a catalog of different interrupts and which routines are used to address them. The IDT will supply the address of the low-level routine that handles that particular event, and the kernel will save the state of the interrupt process on the kernel stack, and the process state will be restored once the interrupting task is serviced. And that's exactly the same as what we discussed at AS. So the interrupt arrives, you make sure that every state of the current process is saved on the kernel stack, you deal with the interrupt, and once that's dealt with, you reload the process's data back into the main stack from the kernel stack, so you can continue on processing it. Now the interrupts can be prioritized using the interrupt priority level, which are often numbered from 0 to 31, and a process is only suspended if its interrupt priority level is greater than that of the current task. Now the process with the lower interrupt priority levels is normally saved in the interrupt register, and it's serviced when the IPL value falls to a certain level. And that actually makes sense. For example, if you get an interrupt priority level of 31, which is a power fail interrupt, you want to be dealing with those first because they're very critical to the operation of a computer compared to something that might come across from a user input. Some common examples of IPLs include 31 for power fail interrupt, 24 for the clock interrupt, 22, 23 for input and output devices, and so on. Now you don't need to remember these for the exam, this is just for reference only. What you do need to remember is the process of what happens when an interrupt is received and what is the operating system's response. So that block diagram on the right hand side of the screen is very critical. The moment an interrupt is received, other interrupts are disabled so that the process that deals with the interrupt cannot itself be interrupted. The state of the current task or process is saved on the kernel stack. The source is identified. Is it hardware, exception, or a trap? The priority of the interrupt is checked. The system now jumps to the interrupt service routine that deals with that particular interrupt. And once completed, the state of the original process which was interrupted is restored using the values which were saved on the kernel stack. And the original process continues. Now, after an interrupt has been handled, you need to enable those interrupts again so you can get future interrupts. Remember, we disabled them in step 1. And that's all you need to know about interrupts and OS kernels. That brings us to the end of this particular lesson. Hopefully you understand how scheduling mechanisms work, FCFS, SJF, SRTF, and round robin. You should be able to calculate the average wait times for processes, and you should be able to explain how interrupts are handled in an operating system through the use of the kernel and the kernel stack. You should also be able to explain the role of the interrupt dispatch table and what is meant by interrupt priority levels. That's all for this lesson. I will see you in the next one.